And we've got a guest speaker, and I might actually invite Holger Meyer, School of Architecture and Civil Engineering, to provide a short introduction of our guest speaker. So over to you, Holger.
Thanks, Seth, and it's an absolute pleasure to have Saman visiting us. So just a brief, I've known Saman since his PhD days. He did his PhD with my good friend Brian Tolson at the University of Waterloo. And so when I visited Brian there, we met, and we've been in touch ever since and working together on a number of papers. I visited Saman in Saskatchewan, 2018, I think we just worked out, maybe, a long time ago, maybe. And so Saman's just recently moved to Australia with his family, going to ANU towards the end of last year. And so it's a great opportunity, I guess, to hopefully work more closely together. And I think just Saman's done a lot of different things. What I really value about Saman is, one of the things I value about him is just his first principles approach to everything. I mean, just looking at a problem and then reimagining it, whether it's the neural network stuff you've done, whether it's, around optimization or the sensitivity analysis. Yeah, you've got a great mind, and I really love and appreciate working with you and just getting those different perspectives. Not great having you as a reviewer, because good feedback that way. But no, it's really a pleasure to have you here, and really looking forward to your seminar. So yeah, thanks, Saman. Yeah.
Cool. So I'm just going to share screen quickly. So hopefully we get the technology to work. What am I doing? This is different to share screen. What is different to usual? Okay, just for the online people, can you see the PowerPoint presentation? You can't see you anymore, so can someone just say a yes if you can see it?
Yes, we see it.
Oh, cool. Thank you very much. All right, everything seems to be working, so I'll hand over to you, Saman.
Okay, thank you very much, Holger, first for inviting me and Seth for hosting me and running this seminar. It's a privilege to be here after a long time. Of course, I was very well aware of Adelaide and folks here since early 2000 when I started my master's degree back then in Iran, working on neural networks. In particular, Holger Meyer's and Graham Dandy's work were kind of my guiding research, basically when I developed my master's thesis back then. And I'm very happy that we moved to be a friend of Holger, in particular because he was my role model initially. And yeah, I had the privilege of hosting him. But you know what, now that he brought up that review or issue, I should say, all I did to Holger, I just returned the favor. Because I was a PhD student. I submitted a paper to WR, but three, four reviewers, and one of them was just nuts. Very nasty. Pages of criticism. This person is, I'm gonna kill him. And of course, it was anonymous at the time, but just a few days later, and he wrote an email to me, hey, Saman, and Brian, it was me, sorry. Anyways, that led to big improvement of my paper. And since then, basically, I'm just trying to return the favor. And just, I wanted him to feel how it feels like when you give that kind of basically hard time to people. So I'm hoping everyone can see me also online. I'm quite far, but yes, I'm here with some pretty ambitious title that I don't think I can ever cover. But anyways, it's there. And yes, as Holger said, I'm now with Institute for Water Futures at basic Australian National University. I'm still learning a lot about Australian landscape. And I'm still very naive to talk about issues here. So perhaps I'm taking you to Canada for the next half an hour or so. And by the way, how much time do I have?
Half an hour. Yeah.
Half an hour? Okay. So I'll try to finish in half an hour, 35 minutes. If I didn't, feel free to kick me out, but be gentle in doing so. But for last week I watched Oscars, I shouldn't have. But anyways, That reminded me of what happened a couple of years ago. So yeah. So just that I still don't have fear. Just some minor signal to work out. And before I begin to my content, I just want to congratulate to our Persian Iranian community, hopefully in Adelaide. I don't think there's anyone from Iran in the room, but there might be some online. And by the way, these are people, so wherever I go now, there was a lot of Iranian folks, seems to be been colonizing everywhere, but not here. So today, just a few hours ago, equinox happened. And that basically marks the beginning of spring, of course, in Northern Hemisphere, sorry. But it's a very special day for people from that region, not only Iran, people from some other countries in that region. And you know, on the very first day, it's a big holiday. I'm here presenting, anyway, I guess my bad timing. But just to let you know what that is, basically it's a kind of celebration that kind of mixes Western New Year and Thanksgiving. So festivities are kind of a mixture of both. And yeah, family members get together around something like this, a table like this called Hafsin. And there's a lot going on in their homes these days. So on that positive note, I'm going to tell you that we are in trouble. And I guess, sorry, by we, I mean Canadians. Of course, Australians are doing very well. This is what's happening there. Unless everything is sorted out here. But anyway, so there is all sorts of issues apparently in Canada. Flooding is a top one every year or every other year. There is some major flooding across the country, and I'm learning in Australia as well. And you know, just this past winter in 2022, what happened in Vancouver and when I was living there, so basically flooding happened and it cost billions of dollars of property damage, road damages, multiple people died, and Vancouver was cut off from the rest of the country for more than 2 weeks. And I was there, my brother's home got flooded and there was no gas, so in gas stations for a couple of weeks. So whenever you go to gas station, you had just some small entitlement. So anyways, big crisis still in Canada. Of course, compounded now with extreme wildfires that happening there. Of course, this past summer, again, we had some, not this summer, the one before, there was major ones. And again, drought, perhaps like in Australia, and people, when they think of Canada, they think of the water country. It's not the case. That's the wrong impression people have, even Canadians. Western Canada, Midwest Canada has some major water stress. And that's the food basket of Canada, a major one for the world. And there are some significant droughts happening every few years with significant impact on agricultural production in particular. Major water issues, water quality issues, in particular for local communities, in particular indigenous communities. So big thing now in Canada. And of course, climate change. Canada is losing cold. Generally good news for Canadians, but not good for the rest of the world, as I'm going to be talking about. So for example, last 30 years, we've lost about 6.5 degrees cold. And you know what, warming has been primarily happening in winter time. And I have experienced that in the past 15 years, 16 years that I've been living in Canada. And that has caused significant damages to things like infrastructure. Just look at that road, basically due to big land subsidence as a result of permafrost thaw. And if you don't know what permafrost is, I'm going to talk a little bit about that. And glacier retreat as well. So based on our base projections, we're going to lose a lot of major glaciers in Canada, and that are prime source of water still in the Rockies, headwaters for example, Canadian prairies. Anyways, Canada is now a host of issues around water. And with that kind of problem landscape, we had some grand vision a few years ago. That's still running, and that's still a vision. Not much of it has really materialized, I would say. But that's about convergence and integration. So a group of us, about 2016 or so, came together in Canada and wanted really to run some, hopefully truly transdisciplinary work, trying to bring the field of climate science, hydrology, water quality, and toxicology, economy, social sciences, indigenous knowledge, computer science, mathematics, and others together. And all happened thanks to Global Water Futures. And basically, we set up this integrated modeling program for Canada that is basically ending in a year or so. And we've been trying to basically couple the really different disciplines and their models to enable the representation of feedback mechanisms. And in particular, positive feedback loops that might emerge and we often ignore because we have that still reductionist approach to scientific discovery and policy support, trying to come up with a rather narrow boundary around things, very engineering, and basically try to solve some issue here. And then we ignore the interaction with the rest of the world. Of course, there might be some unintended consequences somewhere else that might come back to your system 10 years from now, 20 years from now, or eventually it will come back and get you. That's a good news, of course, for engineers. If you have ever worked in consulting engineering industry, that's something good because I worked there, you know, because so you solve some issue and that creates some other issues 20 years down the road, no one come back and you blame you because it's very hard to identify who is to blame. But you're going to get a follow-up project in 20 years. So in general, but anyways, we've been trying to change that. And I had a very good conversation with Seth this morning about that. And he's been doing great stuff on that front as well. Anyway, so this is the big picture. So I thought in my time, I'm going to be covering part of hydrology climate model and part of water resources economic modeling. So many of us do hydrologic modeling. And this is just one example, physically based hydrologic modeling that we've been doing. But there is still a lot of issues that we somehow tend to ignore. And we still have, although we call these models physically based, and we try to simulate basically all the physical principles that we are aware of, we have some big unsolved issues. And just take an example here, the impact of warming and the big extrapolation. So we develop these models, but we run them under scenarios that take the model well beyond the knowledge base and data information that they have been built on. To basically better explain what I mean, let's take a look at the seasonality of temperature in Saskatoon. And this is where I've been based for a long time. And what you're looking at is the average temperature in Saskatoon, basically for different months. And as you can see, temperature hovers around 0 degrees Celsius. So, and that envelope is the envelope of variability. And for example, if you compare that to what's happening in Paris, pretty much it stays above 0. Of course, European hydrology is very simple, I would say, compared to Canadian. But so what's happening is just this threshold is hovering around 0 degrees Celsius. Why? Because in Canada, then it gets you to freeze-thaw cycles of the soil. But what do I mean by that? I mean, there is a time in the year, for example, in March, April, that soil basically melts. And you know, before that, soil is frozen. It means land surface is impermeable. And at this point, it thaws and it begins acting like a hydrologic unit, like real soil or soil that you see, for example, in Canada, in Australia. And you have this summer season at some point again, it gets frozen and again it becomes like impermeable land surface. So this adds a lot of complexity to your hydrology. And here is what's happening now under future climate. Just what I'm doing, I'm pushing this seasonality up 2-3 degrees, and as you see, the timing of freeze thaw changes. And if you don't properly account for this process, for example, your model won't do any credibly under any future climate scenario. That has been our challenge here in Canada, and we've been working hard to fix it, to represent that kind of seasonality problem in the model. And the only way to do it is going beyond hydrology and water balance. You have to have a good account of energy balance as well. And things get worse when you move further north. So that is the permafrost thing that I mentioned. So basically, if you haven't heard of it, permafrost is basically a layer of soil that remains frozen all year round. And you see a lot of that in Canada. And this shows, for example, just an example cross-section. So you have an active layer at the top and then ice underneath. So it could be fully saturated, like this ice wedge that you see, or it could be unsaturated ice. So then you have to account for basically phase change of water in your soil. And what is quite complex is basically this is a temperature profile, a typical temperature profile of a layer of soil like this. Basically soil temperature, depth of soil. So this is the land surface. As you go down, the temperature changes, right? And so you get this fluctuation in a year. So you have active layer thickness, and this is basically hydrologically active soil here. So in summertime, water can infiltrate in and move around just like regular hydrology, but you have like a bedrock here. Water cannot penetrate any further into ice. And in winter, it gets frozen. So this area gets frozen in winter again. Now, under climate change, our active layer thickness is expanding. So we're going further and further down. So the hydrology is changing in big ways. It's already started changing in big ways. And how come you can represent that in hydrologic model, typical hydrologic models? So you have to have a dynamic hydrologic modeling that even changes your active layer thickness. And the only way to do it is to solve water and energy balance of the soil together. And why does it matter? Because permafrost underlies 1/4 of Northern Hemisphere and half the size of Canada. And if you don't know, the volume of methane and carbon dioxide stored in permafrost is estimated to be about twice as much of those greenhouse gases in the atmosphere. So if permafrost melts, then it releases all those gases, and that creates positive feedback loop to further accelerate warming. And here is basically now just a fact that everyone knows, this is the future of permafrost. And this is based on our simulation for a representative permafrost watershed in Canadian North. So you can see that, of course, we have different estimates of current status quo of the permafrost. And of course, we can look at different SSPs, basically shared socioeconomic pathways, and this is the most optimistic one, by the way. And you can see the range of uncertainty under different GCMs or Earth system models. And even under a very optimistic socioeconomic pathway, there is possibility of losing the entire permafrost always, or basically lose, most optimistic case, lose a big part of it. So this is going to have major impact on the hydrology of not only north of Canada, also the rest of the world, because it's connected to the rest of the world through atmosphere. But is only the temperature increase to blame permafrost thaw. So when we think of warming, for example, melting ice, permafrost, we often think of the heat or basically temperature increase, but that's not the only thing. Second prime suspect in the north is changes in precipitation regime, basically compounding impact of precipitation change and temperature. And what's the big deal about it? Almost all GCMs suggest that we're going to get more precipitation in the north, both in summer and winter. And what I'm showing here is just for a representative watershed, what 10 different air system models are telling us under the three basically socioeconomic pathways, an optimistic one, a very optimistic, a very pessimistic, and some middle of the road thing. So, and on the x-axis, you see the changes in annual temperature. So different models suggest that it might be, and this is the last 30 years of the century, from 1.5 to almost 10 degrees warmer in the north. And this one is the change in precipitation. And basically all of them show increase, but some to as high as 50% precipitation increase in the north. What does that mean for example, hydrology and permafrost thaw? So what I'm doing here, I'm just using a machine learning technique to basically infer some contour map that tells me percent of permafrost loss for these different models. And as you can see, so we begin, for example, from 60, 70% here of current permafrost up to more than 90% under these different basically possible futures. And of course, the contour lines are sloped, meaning delta P has an impact in addition to delta T. So let's now look at cross sections of this model. So if we take the cross sections of that contour map, we will see this. First, just look at changes in delta T from 0 degrees to about 10 and permafrost loss. I'm talking about the red curve here, change in T. And of course, you see basically a big increase in permafrost loss in response to only change in temperature. While and this is this cross section basically, right? So delta P hasn't changed yet. So we assume P doesn't change in the future, only T. And of course, it's going to have a big impact. And the envelope is the range of uncertainty, basically derived from this model. And the blue one is change in P only. So I'm talking about a vertical cross section here. So temperature is going to be at 1.5, but different P values. As you can see, you're going to see a lot of permafrost thaw only because of more precipitation. I'm going to get to the processes. And if we increase them both, delta T and delta P, a cross section like this, we're going to see the black curve here. And that's the compound impact of change in T and change in P. And why is it happening? So when we get more P in winter time, for example, it means what? It means more snowfall and more snowpack. So definitely, if you go to the landscape, you feel, oh, it's colder because, or whatever, we're going to get more snow. So it might be good, but it's not, because snow is acting like a surface insulator. Assume that you throw a big blanket on the land surface. That insulates basically the land surface. And in winter time, basically the land surface cannot release heat to the atmosphere because it's a big blanket insulating it. So you get more snowpack, but it's basically boost even the the thaw of the permafrost. And in summertime, when you get more precipitation, again, what happens? When you look at both energy and water balance, so energy by itself is can very gradually basically move to a solid, basically solid particle, basically soil. But as soon as you add more precipitation to it, water can move fast. Now we get warmer water and more warmer water in summertime. So water can basically more quickly transfer the heat into deeper layers. So all these compound the impact of each other, and we get very more warming. And what about changes in seasonality? Of course, changes in seasonality is, of course, very important and another prime suspect here. And this is basically based on some analysis that I'm going to be talking about. I'm looking at sensitivity of permafrost loss to summer temperature, summer precipitation, the blue one, winter temperature, dashed red, and winter precipitation, basically dashed blue. So basically, we are here trying to attribute the changes in permafrost to these 4 factors: summer and winter precipitation and temperature. And as you see here, controls of permafrost loss change over time. So summer temperature is, of course, dominant from the early on throughout the century, and its impacts gets higher and higher. Summer precipitation for most of the century comes first, and summer precipitation, why does it matter? As I said, because now weather is warmer and you get more water. So basically you have more warmer water penetrating, or basically dragging heat into the land surface. And winter temperature generally doesn't have much of impact here, but towards the end of the century, it's becoming more and more important. Why? Because then you get, of course, you get more precipitation in winter time as well. But gradually we have that precipitation phase shift as well. At some point, we get more rainfall than snowfall in winter, in particular the early months or late months of winter. And winter precipitation here, as you see, it doesn't have much impact. And we can do, for example, same sort of analysis, of course, with our hydrologists at the end. We can also look at the impact on a stream flow. And again, the plot that I showed to show you is looking at the sensitivity of winter flow to the same factors plus the permafrost area that is changing as well, right? Because we're losing permafrost. And as you see, early on in the north, the dynamics of permafrost are primarily, that is the prime control of winter flows in the north. But gradually it loses its role. And that's the point that permafrost has caught enough, has gone to way deeper layers that doesn't have much control on winter flows. And at some point, basically, summer precipitation takes over winter flow. Anyway, so we can talk about these further. By the way, how we came up with these plots, for example, I didn't talk about the methods here. And basically, this analysis was made possible by DVARS, data-driven variogram analysis of response surfaces. And if you haven't heard of it, you can check out our website here, vars-tool.com. So we've been, for the past 10 years or so, we've been working basically to develop a new framework and software platform for doing sensitivity analysis called VARS. And the classic way of doing sensitivity analysis is when you have a model. You don't always have a model, though. For example, in this case, yes, there is a physically based model behind this, but you don't have control on these things. So basically, we have just got a set of scenarios out of the model. So we needed to have some sensitivity analysis tool that can work on any given data, and that is what we refer to as data-driven VARS. So I'm going to change gears now and move to the second topic. And basically the role of human, of course, you have to include that here into the equation. And that's what we've been doing in Australia. So this is just a screenshot of a very complex water resources model that we developed for Saskatchewan River Basin. And people typically don't believe that what's happening in Canada because not densely populated. But just in Alberta and Saskatchewan, we have 50 plus reservoirs from small to big, very, very complex water resources system with major transboundary water agreements between provinces and also with the US. So this model accounts for those, and that should be a familiar figure, I guess, for people here. But we have been trying to adopt a hydroeconomic approach, a real one, by trying to couple basically the true economic model that accounts for economic principles like equilibrium, partial equilibrium, general equilibrium, that kind of things, and basically to couple that with our water resources model. And we basically wanted to bridge local scale water operations to all economy, basically river basin economy, GDP, and so on. And why did it matter to us? Because traditionally, water resources engineers only look at direct water using sectors when we do their cost benefit analysis. And that means hydropower and irrigation. But of course, and there are some other smaller sectors as well. But that's only a small part of the economy. For example, for Alberta and Saskatchewan, direct water using sectors only constitute about 30% of the economy. So what about the rest of the economy, non-water using sectors? Of course, they are connected to the rest of the economy through intersectoral transactions, interregional transactions, and we cannot ignore those. So we developed a hydroeconomic model, basically led by my colleague and friend economist, Roy Brower, and with a basically co-supervised PhD student, and that enabled us to look at a lot of interesting things. And here's an example. So there was a big policy question in Saskatchewan, and still is. So Saskatchewan started a $4 billion investment for irrigation expansion just a few years ago. And that is the largest ever government investment in the history of the province, and quite big one compared to everything. The population of the whole province is just over 1 million people. So, and that is about to happen, what's happening here. And for example, when you couple your water resources model with all the details about their plan with an economic model, then you can see, for example, the economic benefits to different regions and to different sectors. For example, these numbers are in million Canadian dollars based on 2015 prices. That investment is going to basically yield $240 million a year of benefit to this region of Saskatchewan, for example, and that's basically where the investment is happening. But for example, in Alberta, it's going to have a big economic boost as well, 77, through intersectoral and interregional transactions. And you can look at all the details. For example, irrigation expansion is going to contribute around $1 million to information and cultural industries in Alberta, just through intersectoral interregional transactions. So that's when water moves upstream. So, so anyways, this has enabled us to look at these things and way more. For example, if you look at the bigger picture, you want to look at classic water resources problems like irrigation shortage, different criteria. You want to look at transboundary water issues, economic impacts like dollar values, ecological impacts, environmental flows, and now something very important around indigenous communities. And this kind of integrated platform, of course, could help you with that. So what we did here, we basically had a big survey and text analysis trying to collect all the policy options in the policy discourse of the two provinces of kind of options or ideas that people have been thinking about, different basic stakeholders. And we tried to run them through this integrated model under 5 different climate scenarios, the baseline climate and 4 other ones. For example, when part of the basin is dry, the other part is wet, or the opposite, or when both parts of the basin are dry or both parts of the basin are wet. And that could, I'm not going to get into the details of the results, but that helped us, for example, to look at different sorts of trade-offs under different policy options and under different climates. Just going fast forward, so this way you could basically look at trade-offs between classic indicators of basically water resources, GDP type metrics, transboundary water problems, ecological problems, and that's again this part was led by my ecosystem biologist colleague to try to come up with indicators that make sense from their point of view about aquatic health and bring that into the equation. And the indigenous aspects was, I would say, was a very quite complex and challenging one. And I'm going to tell you why. Because as you might know, Canada has been trying too hard in the past 5, 6, 7 years on reconciliation through this government has put out a lot of investment funding to basically reconcile indigenous culture and Western culture. And so just before they were absolutely voiceless, in particular when it comes to water policy. But still, there are major issues, although the government keeps pushing for this. What's happening on the ground is terrible. Anyway, so we have a big inland delta. This is, again, map of Saskatchewan River Basin. Here we have the largest inland delta in North America, a major source of biodiversity. And that's the best destination, by the way, for the American wealthy hunters. They can pay as high as $30,000 to hunt a bear. So there has been a lot of impacts, negative impacts on Saskatchewan River Delta here. And of course, beyond the environment itself, that has been the prime source of income for indigenous communities living there. So they've been traditionally doing hunting, fishing, trapping in that region, but it hasn't been possible, at least the way that they used to practice their life. And of course, when it comes to cultural flows, it's very, very difficult to quantify those. And as soon as you want to quantify them, I mean, you may get some pushbacks from the indigenous communities because they have a very different ontology. For example, we always talk about ownership, water rights, who owns what. But North American indigenous people, they believe we belong to water and land. So water has its own spirit. You can never talk water right, for example, to them, or you've basically ruined all the trust that you've been building. Anyway, so it got to a point that First Nations even declared sovereignty over Saskatchewan River Basin just a couple of years ago. Of course, it was very symbolic; they have no power. But we've been trying hard in the last 5, 6 years to basically bring that into the equation, and we've been running, for example, Delta Dialogue Network very frequently with them, and we've been able to build some trust, and that has been very helpful. But this is my last slide on my results. We have a long way to go still when it comes to cultural flows, because this plot shows us what. So this red dashed line is natural and naturalized flow in Saskatchewan River Basin, average, basically, seasonality. And of course, the harm that has been made is irreversible, even with any policy option or climate change scenarios that we might face. So compared to that red, this one, base climate scenario. So if the past climate is going to recur in the future, and every curve there represents a different policy option that has been being discussed in the region. They will be, as you see, of course, you see some variation, but they are of limited help to basically help us get a little bit closer to what they used to have. And different, basically, bunches of curves represent different climate scenarios. And basically what this plot tries to tell, I guess, is that the current policy discourse is really unable to help much with improvement of the status quo when it comes to environment and cultural flows. And if you want to do anything about this, you have to take more aggressive approach and basically invest more or sacrifice or whatever. So what? Any lessons learned? So what I presented was a small piece of a big project that I showed at the beginning, integrated modeling program for Canada. Many people involved, and of course you may refer to the website, look it up, INTCGWF, and you can look at the list of papers, contributions, and so on. But I tried to just summarize what I had learned personally. And you know what I should say, I was very naive at the beginning, overly ambitious on the kind of things that I could do or we could do. And that was primarily, I guess, because of my very engineering brain that I had, wired very linearly. Basically, you're a problem solver, you could come up with numbers for everything, but that turned out to be untrue after working with social scientists in particular for some years. And these are my lessons. Integrated modeling is a process that never ends, by the way, that moves you away from your conventional, rather prescriptive view of modeling, established assumptions, rules, and expected behaviors, to some explorative view. So that's why our models are not predictive that much. They just helped us to better understand feedback mechanisms and what might emerge under different scenarios, rather than to come up with some number to give to your client or stakeholder to design something. The second one was something that I faced quite a lot. Integrated modeling can push the parties involved to the limits of their disciplinary comfort zones, because we have different semantics, worldviews, skills, and terminologies. What I couldn't believe a few years ago was just the fact that how engineers and economists have different language and understanding of the notion of uncertainty. Very Western, right? But you know what? We just speak different languages when it comes to uncertainty. And of course, when you talk to atmospheric scientists, I have a lot of good examples to tell you. Biology is the same, social scientists, very different view. So anyways, it needs some hammering and flexibility and so on. And the last one, so what we do, we just try to inverse our reductionist approach, basically. You have to basically inverse the Occam's razor. And Occam's razor, of course, has been our guiding principle for science discovery, policy support, engineering, and so on. The only way to solve the issues is convergence. Through convergence, basically, that's to me is the inversion of Occam's razor. So I guess I leave it here. You know, if you have interest in my type of work, I have a YouTube channel now, and with some videos. And by the way, so there is a playlist on sensitivity analysis, VAR stuff that I mentioned, some tutorials and so on, and of course some on machine learning stuff that I've been recently doing. You may follow me on Twitter, and that's it. Thank you very much.
Thank you. I might stop sharing if that's okay, because then we can see our online colleagues as well. Wonderful. So thank you for a fascinating presentation. There is a bit of time for questions, so if anyone has any questions, Angus.
The 4 billion you talked about in terms of expansion for irrigation, what was the objective? Is it to export grain overseas, or because presumably Canada is meeting its food needs currently? So what's the rationale of a major expansion in agriculture?